Okay, you already covered the previous example, which asks you to find phi of n up to n is 30, right? And that one was just by checking each integers less than or less than n for each n, right? And it asks whether you can find some kind of patterns for when n is prime or composite. This theorem is a conclusion of it, right? So if n is prime, then phi of n must be n minus 1, and vice versa, right? So we need to prove two directions, right? Okay, first, let's say p is a prime, then every positive integer less than p is relative prime to p, right? That's clear. So there are p minus 1 such integers. You can say phi of n must be p minus 1. So one direction is easy. How about converse of it? Then if we want to prove if phi of n is n minus 1, then the n must be a prime. So listen carefully. We want to prove with this condition we got that. But instead, we want to prove contrapositive of that statement. So let's take the negation of that one. So n is not prime, then phi of n is not n minus 1. Okay, so if you can prove it, then that proof is also the proof of this converse of this statement, right? Okay. So let's assume p is not prime. Then p should be 1 or composite number. If p is 1, then phi of p should be 1, because by the definition of phi of n, we are looking for the positive integer not exceeding n. So there is only one integer, which is 1, is positive and not exceeding 1. And 1 is relative prime with itself, because greatest common divisor of 1 and 1 is 1, right? So we found one such integer. So phi of 1 should be 1. But if p is 1, then p minus 1 is 0, right? So phi of 1 is not equal to 0. So this part we prove if p is not prime, then phi of, it's a kind of 1 is not prime, clear, then phi of 1 is not 1 minus 1. We prove that part. Okay. Then the second part is when p is composite number. So let's say p is composite, and the meaning is p has a divisor d, which is between 1 and p and these are not relatively prime. Maybe d itself is the greatest common divisor of these two, or there might be some greatest common divisor which is not 1, right, for these two numbers, right? Then because the n needs to 1 up p minus 1 integers from 1 through p minus 1, say it's d itself, is not relative prime to p, right? We already found it. So clearly we don't know the exact number of phi of p at this moment when p is composite case, but clearly that number should be less than p minus 2, because we are not going to count the integer d to satisfy that condition, right? Then that is enough to saying phi of p is not n minus 1 or p minus 1 in this case, because phi of n should be less than equal to n minus 1. So n minus 1 is kind of possible maximum number to become phi of n, because if you just choose any n, then there are only n minus 1 kind of positive integers which could be relative prime with n, except 1. That's why we separate these two cases, right? So if p equals 1, phi of 1 is 1. That's clear. But starting from 2 is relative not relative prime with 2 itself, right? So possible number of integers which is relative prime with n is n minus 1, right? So n minus 1 is possible maximum number for that, and if phi of p should be less than equal to p minus 2, then it's clearly we can claim that phi of p is not equal to n minus 1 or p minus 1 in this case. So for both, no matter whether p is 1 or composite number, it's clear that phi of p is not going to be p minus 1. So we can claim the contrapositive of it. So if phi of p is p minus 1, then p should be prime. So by that, we prove this direction of the statement. So from both this part and that part, we prove this theorem.